Cool. So today, as y'all can see, we're going to be talking about recommendation engines. I made this a while back. I feel like I was still like a kid back then, so it's very like childish fun. But anyways, so today we're going to talk through three main kinds of recommendation engines. Talk about the concepts behind each one. Talk about pros and cons, and perhaps when we're going to use which. So the main three types of recommendation engines we have here are non-personalized, content-based, and collaborative filtering. When you're talking about recommendation systems and when you're explaining your project to someone, maybe like an interviewer in the future, maybe you're just like talking to some other data scientist about something that you built, you want to mention if your recommendation system is a content-based kind or a collaborative filtering kind. So we'll talk through what these mean in a little bit as well. So recommendation engines are super important. Some examples, I don't know, most recently I was using Amazon, Spotify, Netflix, Facebook ads, which have targeted me really, really well in the past year. Those are also recommendation systems. So let's talk about the very first one, non-personalized recommendation engines. You might think that, yeah, this sounds very, very simple, but it is still very useful. The idea of non-personalized recommendation engines is that everyone just gets the same recommendations. Very, very useful for if you're a brand new business with no data. If you really want to like push out like a product or a recommendation or an item to someone that, you know, maybe that's like your highest ROI product or something like that. Those are all valid reasons to use non-personalized recommendation engines. This is also a really good tool that you can use to actually gather more data for your company, product, whatever it is. So it might seem very simple because it's very easy to make recommendations. Like literally, if you're thinking about it in like a pandas way, maybe like you sort for like the most popular item, push that out, but can be very valuable. One example that I have here is when you sign up for a new YouTube account, they just give you like the trending videos. So that's an example of non-personalized recommendations. No machine learning, barely any data science going on behind the scenes. So is it the most effective? It's not personalized, but again, based on how much data you already have, it might be effective. All right, so just quickly to know that this is actually a group of recommendation engines. All right, next is content-based recommendation engines. We're not going to go very in-depth into like the algorithms behind this because you've already seen a lot of the algorithms that do content-based recommendation engines. So the idea behind content-based recommendations is as long as you're making recommendations based on an item's features, that would be content-based. So models that we already know can totally do this. As an example, let's just say we have this data of like a bunch of movies, and for each movie you have genre, actor, director, maybe like IMDb score, Rotten Tomatoes rating. This is the kind of data that you should have to build a content-based recommendation engine. So using some models that we already know, even back in phase 3, let's just imagine, okay, let's use movies as an example. Imagine you have a Netflix account and you're watching a bunch of movies. If you were a data scientist at Netflix, you have information on what people watch or don't like as much on Netflix. Maybe you use things like how much of a movie they watched before they like stopped watching. Netflix also has a thumbs up, thumbs down. You can use that to build a classification model for a user, right? Like if you have enough data on like, okay, this person likes movies A, B, C, D, doesn't like so much like TV show 1, 2, 3. You can use that to train some sort of classification model like you did in phase 3 to come up with somewhat personalized content-based recommendations for a specific user. So classification models, which is what you all did last phase, very, very applicable here. One downside is you don't often have that kind of data. Another kind of model that you might use, nearest neighbors. So nearest neighbors, I think in the context that you guys have talked about, you talked about nearest neighbors in terms of KNN and classification. But the whole idea of KNN is looking at what's most similar, right? So if you think about, okay, let's say I have this data frame of movies, and I have like the Avengers as a movie there. if you know that someone likes the movie The Avengers, what are other movies that they would probably like? Based on these features, well, the other Marvel movies have the same genre. A lot of them have the same actors. I know a bunch of them have the same director as well. Just looking at those similar features, and also if you think about it in the K nearest neighbor sense, when you're looking at in the feature space, how far away each data point is from each other, just recommending movies that are closer to each other, movies that are nearer neighbors to each other is another very quick way to make content-based recommendations. And this doesn't require you to have a lot of historical data on a single person. You just need to know at least like one thing that they like, and then you can recommend something else. So even though y'all have done that like K-nearest neighbors and scikit-learn, within scikit-learn, there's actually like a nearest neighbors package, like only nearest neighbors, where you can feed it in one data point and it'll literally give you back like the 5 or however many nearest data points you want. That's a very, very straightforward content-based recommendation algorithm as well. Finally, you can also do clustering here. I think clustering is something that y'all talked about maybe a couple topics ago. You can cluster your movies. And if you know that someone likes something in one cluster, just recommend something from that other cluster. So using a lot of the tools that we already know, you can actually build content-based recommendation engines already. Cool. I'm going to take a quick tangent here to talk about similarity metrics. So in content-based recommendation engines, the whole idea is you're comparing content. So you're comparing data points to each other, and each data point is usually like an item, or in this case, a movie. There are many different ways to calculate similarity metrics. Again, you can sort of think of this as like your hyperparameter tuning for something content-based. Whether you want to define your similarity using, I think the most common ones that we've talked about are cosine similarity and Euclidean distance. They're just two different ways to measure distance and how similar or different points are. This is something that you can tune. Another tangent to go off of this, how can you validate your content recommendations, right? Like, let's say I have a Netflix account and I like watched all of the Marvel movies, and then they start recommending to me like those other superhero movies that maybe aren't as good, but you know, because of the content-based recommendations, they figure that, okay, this person must really like superhero movies. How the model has no idea whether I will like other movies or not, and there's no way to verify that. Of course, you can verify it after the fact, like whether, let's say I start watching this other movie and then I stop watching like 5 minutes in, but validating content-based recommendation engines get a little bit trickier. There's actually no way to validate or verify that your recommendations are good until you actually see how people react to them. So do keep that in mind if you're building some sort of content-based recommendation engine. Cool. So a little bit more about that. What are some pros and cons of content-based recommendations? The main one is kind of similar to what I mentioned before. This has a funny backstory from like 2 years ago. Is I bought one plant and it died, but Amazon just kept recommending me plants to buy because Amazon had no idea that I just failed as a plant owner. So the main con of content-based recommendation engines is you get what's called you just get very specific content. You start to get pigeonholed into the things that you end up consuming, especially if you just buy something one-off from one website. The data that they have on you is not very robust. Another example, like, yeah, I think I talked about with that superhero movie example. If, let's say I only watched and rated horror movies on Netflix, they might only give me horror movie recommendations. So yeah, that's one pitfall of content-based recommendations. Again, the pro of recommendation engines, the data for this kind of recommendation engine, especially if you're using like a nearest neighbors method, very, very easy to set up. You don't need a lot of like customer data in order to set up this sort of engine. Cool. Any questions at this point? Because we're going to move on to collaborative filtering. Sweet. Okay, so collaborative filtering, to start, the data type that we use, or the way that the tables look with collaborative filtering, looks quite different from content-based. So if you remember, prior to this, our table looked very, very similar to a lot of the data frames that we've been working with. Every row is an object, every column is a different feature. With collaborative filtering, the data frame looks kind of different. It's a utility matrix. I'll talk a bit more later. I have some code for implementation. It doesn't actually look like this, but the data looks like this. And I'll explain more what that means later. But the data that you have, instead of having an item's features, you have a collection of existing ratings. So this is called a utility matrix. Every row is a different user and every column is a different item. So in this example here, I know this is a little bit small, but as you can see here, you have users 1 through M, movie 1 through N. What this utility matrix shows is that user 1 has watched and rated movie 1 and N. I'm guessing it's like a scale of 1 through 5. User 1 rated movie 1, 1 out of 5, rated movie N, a 3 out of 5. Same for the rest. So this is just data on historical ratings of between users and items. The whole idea of collaborative filtering is to fill in this utility matrix. Try and guess what users would rate other things and recommend the next highest thing. So with this user 1 example, earlier the user had rated movies 1 and N with a 1 and 3. Whatever, we're going to talk about algorithms in just a sec, but whatever algorithm it went through, you can see that for movie 2, it was predicted that user 1 would rate it a 4, which let's just assume that out of all of these movies is the highest one. And so therefore for user 1, you would recommend movie 2. The whole idea behind collaborative filtering is that these numbers are filled in while taking into account the other users' ratings as well. And I'll talk a bit about a couple ways that we go about doing this. But note that the data is different. Here we only have like a column per movie, and you are not really taking into account like the movie's features at all, really. You are implicitly, later we'll see in the math, but in this case, not at all, not explicitly. Okay, so the whole idea of collaborative filtering, again, based on ratings of other users. We're going to talk through two main ways of doing collaborative filtering. The library that we're going to look at later is called Surprise, and Surprise has algorithms that implement both of these. So there's memory-based methods and model-based methods. I'm going to go through, and within memory-based, there's 2 dimensions that you can do it over. You can look at it via users and also via items. I'll just walk through one. The other one is really just the same thing on a different axis. We'll see in a sec. And then there's model-based, which is matrix factorization. There's a little bit of linear algebra that comes back in, but not to worry. I've broken it down into pictures. Hopefully it'll make it clearer. Okay, so let's talk about user-to-user collaborative filtering. So this is a kind of memory-based method in Surprise, and I'll show you all that later. Some of the models use this kind of method. So let's just simplify this problem, and let's just have this 4x4 utility matrix here. 4 users, 4 items. Actually, in this case, whether the users or the items are the row or the columns, it doesn't matter. So let's just say that we want to find out what the predicted rating is for user 1 and item 3. And let's just assume that, we have all this data. Oh, and something to mention, typically you have a lot of question marks. It makes a lot of sense that most users don't rate most items anyways. So that's known as a sparse utility matrix. And I'll talk a bit more about implications of that later. But for this simplistic example, let's try and figure out what user 1's predicted rating is for item 3. So it's really a 2-step process. First, you get user similarity values. User-to-user collaborative filtering does predicted ratings based on how similar users are. So first, we start by using some similarity metric. In this case, I'm just going to use cosine similarity. I believe that's what the default is for the models as well, but you can actually pick what similarity metric you want to use. I'm going to find the cosine similarity between user one and every other user. And so this is really just me taking cosine similarity between the numbers 433 with 222, 344, and 544. 524, sorry. So basically out of all the items that users have similarly rated, I'm just getting cosine similarity between those ratings. So this is just another table showing that user 1 and 2 have a 0.65 similarity, 1 and 3, 0.76, 1 and 4, 0.83. So user 1 is most similar to user 4. That's what this is saying. What I'm then going to do is I'm just going to take the weighted average of these other users' ratings for item 3. So I know the math sometimes with numbers, it can look like a lot, but you can sort of see that 0.65, 0.76, 0.83 comes from this table here. 454 comes from 454 over here. So I'm multiplying this out, taking a weighted average, and weighted average just means that I'm dividing it by the sum of this to come up with a predicted rating of 4.34. So the predicted rating, if I'm using user-to-user collaborative filtering, is 4.34. I will say this is not the most commonly used algorithm. I'll explain why later, but any questions about the math that's used here? Cool. All right. Some quick pros and cons before we talk about the other algorithms, because it's pretty much the same. These are personalized for each user. So every user is going to have like different predicted ratings, so therefore different recommendations. That's a huge pro. Lots of cons though, not lots, but considerable cons. One is computationally heavy. So just by doing this, yes, we had 4 users, 4 items. We had to do all of this calculation. Imagine how it scales. If I have like hundreds and thousands of users, what Netflix has like, what, 20 million users? Probably, I don't know what the number is, but so many users, so many movies and TV shows, you can imagine just coming up with that predicted rating can be very computationally heavy. There's also popularity bias. So the idea of popularity bias, because you're taking a weighted average of other users' ratings, if a lot of people rated item 3 of 5, this would also be a 5. If everyone else rated item 3 of 5, predicted rating will be 5. So you can imagine, like, if you've ever had an unpopular opinion, that's where popularity bias becomes a problem. Usually in recommendation systems, you don't really care so much about popularity bias, but it is something to just be aware of. Cool. Lastly, the cold start problem. So that's a huge issue with collaborative filtering problems. Imagine if I had no data on user 1. If I'm like a brand new user to Netflix, Netflix has no data to make this kind of recommendation, right? Because they don't even know, I have no data to even start calculating similarity between me and other users. So as a result, I think Netflix, at least when I signed up for Netflix, they made me like rate a few movies at the very start. That is one of the mechanisms that they can use to get over the cold start problem so that they can start making recommendations based off like a small subset first. So if they had zero data at all, this algorithm won't even be able to run. So that's something else to consider. But usually a lot of websites have these like mechanisms where they have you rate something first. I think if you do the lab on recommendation engines with Surprise, they'll actually show you like some code of like, they'll give you random movies and you rate them, and then they'll base your recommendations off of that. So yeah, those are some pros and cons. Now, item to item collaborative filtering is exactly the same math, but instead of taking the similarity of users, you're taking the similarity of items. So pretty much the same thing, just the only thing here is because we're doing item 3, the similarity we're getting here is between item 3 and all other items. So instead of comparing, these numbers as columns, we're comparing them that way. So here we're going to compare 454 to 235, 242, or 244. And then same thing, weighted average. And when you do this all, it comes up with a predicted rating of 3.31, which is actually very different, or depending on how you contextualize different, but Our other prediction was actually, I think, was 4.34. And just by changing the axis of this calculation, we get 3.31. So it's like about one whole entire star off, which however impactful that is, it really depends on context. Like for movies, does it matter if you rate something a 3 or 4? If it's like a restaurant, is that a big difference? Kind of up to you to decide. So when we're looking at user to user versus item to item, some questions come up, which is better in practice. So experimentally, not like mathematically or anything, but just based on people implementing a bunch of algorithms, item to item has just proven to be more effective because it is hard to predict users' unique tastes. You also have to think about complexity. Do you have a lot more items or a lot more users? Those two numbers, if you have like M users and N items, if you have more users or more items, one might be more favorable than the other in terms of how much computational power it takes up. So if you have more users than items, and if anyone's familiar with like big O notation, not super important for data science, honestly, but good to be aware of. If you have more users than items, which would be faster. If you have more users than items, it would actually be faster to do item to item collaborative filtering. Also, another thing with experimentally, for some reason, Pearson correlation has demonstrated to be the best similarity metric. Don't know why either. It's just like a bunch of people implemented a bunch of different ones. Pearson just happens to be the best. But I don't think there's a big difference between using different ones. Cool. The next algorithm is the main one that people use. It's called singular value decomposition, SVD. It's basically another way to fill in the utility matrix via matrix factorization. A lot of jargon on this slide. They're all kind of related to the algorithm that we're going to talk about in a little bit. But what to know is SVD is a model that we're going to be implementing in a little bit. I have some code for that. It is a gradient descent procedure. Therefore, it's not as computationally heavy as, calculating like the user to user, item to item similarity. It's actually faster. And also it's quite mathy, but the best models do use some form of SVD. So actually some really interesting history about how SVD came about is Netflix used to run this recommendation competition. I think this was back in like 2007. And this mathematician named Simon Funk came up with this idea of creating SVD as an algorithm to do prediction for ratings. It's actually a very, very traditional like linear algebra process. Like SVD was similar to, you actually use SVD when you do PCA. You'll actually see that this is called SVD, but you're not doing SVD at all. Just something to clarify. You're not doing SVD in surprise, you're doing SVD in PCA. I'm going on a bit of a tangent. So SVD is the name of the algorithm, but it doesn't actually use SVD. And I'll go through the process and then these words will come back up. Okay, so the whole idea of doing SVD, there's the word decomposition here, decomposition and matrix factorization. If you remember, like, I don't know, like high school math, factorization was used when you have like an algebra term, like an x squared plus 2x plus 1, and you need to split it up into like x plus 1 times x plus 1. That's like representing an equation as like a product of multiple smaller equations. That's factorization. So here we're doing matrix factorization, where we're trying to represent our utility matrix as a product of two other matrices. So why I say this is not actually SVD, real SVD, which is what PCA uses, actually does it into 3 matrices, but this process does it into 2. So the whole idea was trying to represent this, we're trying to represent this utility matrix as a product of an item matrix and a user matrix. So that's how the idea came about. They're like, okay, how can we represent this information as 2 separate matrices? So maybe we can gain some knowledge about, users and items. Latent features, which is something that should sound familiar from PCA. So they're all kind of related. these latent features you can sort of think of as like PCA features of each item and each user. So basically each item is going to be represented by some like random number, like two random numbers that are sort of like PCA representation of whatever they are. So these numbers don't really have any meaning, but together they just represent the item or the user. Something to note is that this one point here, if I'm trying to predict user one and item three, they are going to be impacted by these points here because this is item three, and these points here because this is user one. All right, we're going to get into a little bit of gradient descent. So if you remember gradient descent, you always have to start with some sort of initial values. And just for simplicity's sake, we're going to initialize all our values as one. The whole idea here, instead of trying to fill in this utility matrix, it was found to just be more efficient to try and recreate the utility matrix. And we'll see that the math behind this is fairly, not simple, but it's a lot less difficult than having to, figure out the patterns and all that and to fill that one spot up. They're going to use a gradient descent procedure. So the whole idea here is they're trying to recreate this matrix here using matrix multiplication to match the original utility matrix. So let's just set all of our initial values. So the way that this works is you set your initial values for your component matrices as all ones. You can set it to be whatever you want, but we can start at 1. When you multiply these matrices out, and I know this might be like have to like go back and review. You never have to do this math by hand anyways, so don't worry about it. But the whole idea is when you multiply these matrices out, you end up with a square matrix of 2s. Then how you set the cost function for this process is you look at the difference between this matrix and this matrix. This RMSE of 1.75 is the average difference between each particular rating. So it's really the difference between like this 2 and this 4, this 2 and this 2. It's a root mean squared error of like each point here and each point here. So that's the RMSE of 1.75. How the gradient descent starts working, because this is just the initial values. You start by trying to change one value at a time. So I know there's a lot of new colors here, but let's say we try and figure out, okay, what's the next best value to belong here in this X? If you're familiar with matrix multiplication, and no worries if you're not, if you change this X, it's going to update this whole top row in your recreated utility matrix. So updating this X is going to update this. And you know that the cost function, you want to just compare this matrix here to this matrix here. So therefore, you just have to find the best X to give you the lowest error between this row and this row. And this is really done using like a single derivative. Again, if it doesn't make sense, the whole idea is like, what's the best X to make the smallest difference between each of these numbers? And turns out that if you minimize this equation, which not super important what that is, basically the best X to belong here is 2.5. So best X for this is 2.5. If I replace this with 2.5, multiply it out again, our RMSE has actually gone down from 1.75 to 1.58. So that's kickstarting the gradient descent process. Our cost function is getting smaller and smaller. So what's going to happen is we're going to keep doing this, but not just for like this one value here. For all 8 of these values here, 8 of these values here, we're going to just keep changing up numbers to get better and better. So at some point, none of these numbers matter anymore, but you come up with some recreated utility matrix. This recreated utility matrix gives you predictions for every user item combination. So just so happens we just need this one here, 3.7. So our RMSE has gone down from a starting point of 1.75 to 1.15. And our predicted rating is now 3.7. Something interesting to note, this value of 3.7, if we compare it to our other methods came up to what, 3.3 and then 4.3. 3.7 happens to be in between the user to user and the item to item number. So going back to some of the keywords that were highlighted, this process is parallelizable, meaning that every time you are changing values, you change an entire row or entire column at a time. So that means it's preserving the relationship between, within a user and within an item. So every time you're changing one value here, you change an entire row. If you were to change one of the values in the user component matrix, it's actually going to update an entire column. So that's parallelizable. And this method is called alternating least squares. Alternating least squares is just because this is a least squares way of figuring out the best X. So lots of terminology there. Just want you all to have heard these words before. I think that's what's important. But yeah, we got our RMSE down from 1.75 to 1.15 through this process. And this one, I just plugged it into the model. I plugged these numbers into the model to see what these are. But yeah, I would say if all of this math went over your head, that's okay. Not super important to understand exactly how everything works at this point, but I will say, because I did use this in some of my projects, interviewers do ask if you know how it works. So if you use it in a project, do read up about it for sure. Cool. Any questions before I do the code implementation of these models? Sweet. Code implementation, very, very simple. A couple things that are slightly different. So the library that we're using for these algorithms is called Surprise. Surprise is actually built off of scikit-learn. But one thing to note, you know how in scikit-learn we have our own like accuracy score, we have train test split comes from scikit-learn and cross validation comes from scikit-learn as well. For Surprise, you have to use Surprise's version of them. If you try and use scikit-learn's version, it will not work. It'll just not, they don't interact well together. So if you're doing recommendation systems project, just make sure that you're using the Surprise version of these methods. So I'm going to go through two quick examples. One, I'm just going to use a built-in data set. So this is a movie lens data set. I believe it's the same data set that was used in one of the labs, actually. So I'm just loading this data set, and I'll show you how easy this is. Do my train test split. The one downside is, and I'll talk about this with a real example later, you actually cannot inspect your data frame the same way as you can inspect like your pandas data frames. But the way that you run your model, very, very similar to scikit-learn. You instantiate your SVD, fit it on your train, predict on your test. So if I just run this super quick, there we go. We have an overall RMSE of 0.94. RMSE of 0.94 just means that overall, we are 0.94 stars off. And I'm guessing it's a 1 to 5 scale, so up to you to decide whether that's good or not. To make predictions, you actually use the svd.predict. You give it some sort of user ID and item ID. Depends on how you feed it in, and I'll talk about that in more detail later. But just by doing that, you can come with a prediction just like that. So for this random user, this random item, the real rating was 4, but the estimated rating was 4.28. So the procedural code, very, very straightforward. Now let's use like a real example. So what I was talking about with like the utility matrix, it's actually very, very inefficient to store data like that in a utility matrix. If you imagine like a very, very large version of this, you'll be basically storing a lot of zeros, and that's not very efficient. So therefore, they take more of like a coordinate approach, whereas instead of storing like a m by n table, they just store three columns: what user it is, what item it is, and the rating itself. So this is an example from Yelp. I forget how many I have here. Okay, I have 100,000 ratings from Yelp, from certain number of users, certain number of businesses. And so this information does translate to a utility matrix if you're just like to map out, but this is just a more efficient way of storing that data. Cool, let's find out how many. So we have 80,000 users, 2,500 businesses. Very, very straightforward EDA just to get through it. Lots of 5 stars, cool. Some business IDs were rated 1,600 times. Great, cool. You would do a much more in-depth EDA if you were doing a project like this. To get ready for your data to use in your modeling, several steps that you have to take. Something that's different from Scikit is that Surprise uses a reader object. So this reader object basically helps to contextualize the rating scale so that it doesn't predict ratings above or below a certain number. So give your rating scale in the reader object and just instantiate that, and that's okay. And then Surprise has this load from data frame method that allows you to load in your data through your data frame, taking into account the reader as well. So here I'm taking my Yelp data frame, which is this. And one thing is you have to pass it in the exact order of user ID, item ID, and ratings. You just have to do it in that order. So once that is done, again, the one downside is when you pass your data through any of Surprise's like objects, you are not able to see it, but you can trust that it's there. So train, test, split works kind of similar. You don't have any X or Y here. It's really just train and test. So your train and test, same name of the method as scikit. You can set your test size as well, but now we have our train set, which again, you cannot see, and your test set, no, test set is different from test, but you have your test set, which you can sort of see. Cool. So you can actually also use grid search and cross-validation. I don't have the code here, but it's in their documentation. I'll point you all to those pages in a little bit, but there are a bunch of hyperparameters. These are some of the main ones. And epochs, again, similar to gradient descent process, and epochs is how many times it will go over every single number. So for what that means is like, how many times is it going to go over each of these? So one epoch is going to go over like 16 numbers. So that's epochs. N factors is another interesting one. That's the number of latent factors. So here, each item being represented by 2 numbers and each user being represented by two numbers, that's arbitrary. You can control that. The whole idea is if you have more numbers, you get more like intricate data, but they're just like latent representations. They don't really have meaning. So in this grid search, turns out the best one was 1. Bias, I honestly forget what it is at this moment. Learning rate and also regularization. So if you find there's overfitting, you will just fix your regularization. So instantiate this final model that has been tuned with grid search, and I'll show you all where that is later. You can fit that, test it on your test set, and when you look at your predictions, this is what it outputs. So this is the first 3. Let's just look at the first one. So predictions 0. It'll tell you that for this user and this item, the real rating was 2, but the estimated rating was 4. Okay, this is not a great example, but I wonder what the RMSE is here. Okay, so the RMSE is like a 1.3. So it's about 1.3 stars off. So this being 2 stars off kind of tracks. So yeah, this is how you can validate your model. Let's see, what else? All right, okay, so to make predictions, you have to feed it in the user ID and business ID in the same way that you had it in your data here. If you feed it like a business ID or a user ID that didn't exist, it'll actually just return you the average rating over and over again. So just take note of that. If you are seeing the same rating come out for every user item combination, it's probably because you're not feeding in the right data. But yeah, that's how you use .predict. So you can just use random users. If you have the Yelp data set, you can actually find out what these business IDs are and who these people are, but that you can do through the Yelp API. But yeah, that's how you make recommendations. Interesting. I really like the surprise documentation. I think it's done pretty well. They actually give you the code on like for a particular user, can you get the top however many recommendations? So that's pretty neat. They literally give you that code. For model selection, this is where they give you train test split parameter search is the one I want to show you. You can do grid search as well. So grid search, very, very similar to scikit, just slightly different. So do check out the documentation before you implement it. Finally, the different algorithms. So I talked about the item to item. So the item to item ones are the ones that say KNN. So anything out of KNN uses item to item methods. And then any matrix factorization is matrix factorization. They have a couple like slightly different ways of doing it, but yeah. So they have like, I honestly don't know what the extensions are either. But yeah, implicit ratings, non-negative matrix factorization. I don't know what those mean either, but they're just like different models to try out, like akin to you doing like random forest, gradient boosting. You would try all of these for any recommendation engine. But yeah, also if you just want to see this information in written form, I just threw them into blogs because I did. So that's there. And also something else that's really interesting is there is a class of algorithms that combines collaborative filtering and content-based filtering. It's through this library called LightFM. I've used it a couple times. Pretty interesting results. So if you want to use like collaborative filtering, but then re-weight your ratings based on item similarity, you can do that with LightFM. And a few students I've had do like capstone projects where they incorporate that. So that's been really interesting. But yeah, that's all I had to share for recommendation engines. Any questions, comments, thoughts? Sweet, awesome. Let me